Hi, in this video I'm going to talk about a new way of heat conduction which has not been experimentally observed before. That is, I'm going to discuss about heat transfer via what is called quantum jitter. What do we mean by this quantum jitter? Now, quantum field theory tells us that in vacuum it is possible to have transient particle creation. That is, these particles are not permanent particles, but they are virtual particles, and therefore they are ephemeral. Therefore, we can create something out of nothing. So vacuum is nothing, and we are actually seeing creation of particles in vacuum. So such fluctuations can occur in vacuum, and these fluctuations, creation and annihilation of virtual particles, can result in generation of electromagnetic waves in vacuum. And this is one of the fundamental ideas in quantum field theory. Now, coming to the heat transfer part of this, conventionally, there are well understood ways of heat conduction in matter. For example, in solids, a very common way of conduction of heat is via what is called conduction. In conduction, the particles vibrate because of the thermal energy, and because of the contact, heat is transferred from one particle to the other, and through the whole body, heat energy traverses. So this is via contact. There is another well-known method called convection of heat that occurs due to movement of fluids such as gases and liquids. So fluid movement in a system can cause convection currents, and therefore we know hot air goes up, cold air comes down. This kind of movement of currents is due to what is called convection. And there is another type of heat transfer in objects called radiation. Radiation occurs either in a very dense medium, or like an air, for example, or in vacuum as well. That is, transfer of heat energy through vacuum or low-dense media is called radiation. Here, electromagnetic waves carry the heat energy, and heat energy is transferred. For example, solar energy reaches Earth through the process of what is called radiation. Now, these are very well understood methods of heat transfer. Now, recently, through an experiment, a group at University of California at Berkeley have been able to prove heat transfer via what is called quantum jitter or quantum fluctuations. They have reported these recent results in the prestigious scientific journal Nature in the December edition, December 12. In their experiment, they have built an interesting experiment, a very sophisticated one at that, where two plates of nano dimensions plates are actually silicon nitride plates, silicon nitride coated with gold, thin layer of gold of nanometer dimensions, kept in vacuum, and they've been able to attain thermal equilibrium between these two plates. If these two plates have attained thermal equilibrium, then it indicates that there has been heat transfer between these two plates via quantum fluctuations, and such a kind of heat transfer has not been observed experimentally before, though theoretical predictions have been there. So this is another method, a new way of heat transfer in particularly such small scale devices or nano devices. Now what is happening is very interesting here. Now the entire setup is kept in vacuum, of course, and the dimensions of these gold coated silicon nitride plates are actually 300 micron by 300 micron across. That is about 0.3 millimeter area, and the thickness is only about 0.1 micrometer. Very thin plates, and they are kept at very small distances. We'll get to that later, but the distances are typically not even a few hundred nanometers. Now what happens in this experiment is you have to rule out other ways of heat transfer between these two plates. For example, there could be just radiation from one hot plate to another cold plate, because one plate is kept at a higher temperature, let's say, and another plate is kept at a lower temperature. Now there could be therefore just radiation. There could be other kinds of interaction between these two plates so that heat energy is transferred. Among any of these three mechanisms of heat transfer could occur. But one has to rule out in such experiments all these known methods of heat transfer, and I would say this Berkeley group has successfully done that, going by their results and data. Now what is interesting is, in 1948, Dutch physicist Henrik Casimir discovered what is now called as the Casimir Effect. The Casimir Effect is nothing but generation of an attractive force between two parallel plates kept in vacuum, and if the plates are close enough. Now this occurs because in vacuum, as I already mentioned, electromagnetic waves in the form of quantum fluctuations are created. Because of quantum fluctuations, new particles and fields are created, and this leads to generation of electromagnetic waves, and depending on the distance between the plates, these electromagnetic waves of only certain wavelengths could fit in between the plates, and any longer wavelengths could exist only outside of the two plates. Under such circumstances, the pressure developed on these two plates due to the waves existing outside can create a force between the two plates, and therefore there could be an attractive force acting between these two plates, and this is called Casimir Effect. And this was discovered way back in 1948, and it has been observed experimentally in many cases. Now coming to the experiment carried out by the UC group at Berkeley, they have observed that the heat transfer between these two plates, one plate kept at a higher temperature, another plate kept at a lower temperature, occurs due to what is called a new mechanism assisted by what is called Casimir Effect. That is, in solids, when conduction occurs, heat transfer occurs due to what is called vibration of the atoms present at lattice sites in a solid. Now, the thermal energy is taken in by these atoms and they start vibrating at specific frequencies, and these frequencies are called phonon modes. That is a particular, one can say it's a particular frequency of vibration, and different phonon modes are possible in different solids, and phonons as such are nothing but quanta of lattice vibrations. So these lattice vibrations are quantized. That is, these vibrations cannot occur at any random frequency. These vibrations are quantized, therefore specified frequencies are only allowed for vibration of lattice in a solid. Therefore, these modes are called phonon modes. These modes of vibration, different modes of vibration that are allowed are called phonon modes. So, microscopically, if you treat conduction mechanism quantum mechanically, you would understand that this arises due to lattice vibrations. The quanta of lattice vibration is called phonon, and therefore different phonon modes are possible for vibration in solids. Now, what happens in this specific experiment is something very similar. Now, these two plates are kept at different temperatures, let's say T1 and T2. If they are kept at different temperatures, and if there is going to be a thermal equilibrium between these two plates in the conventional ways, then these two would reach same temperature after some time, and then one could conclude that among these three known ways of heat conduction has occurred. But that is not the case here. The heat bath that keeps this plate at temperature T1 and this plate at temperature T2, they do not reach thermal equilibrium due to the conventional methods. What actually happens is, due to Casimir effect, some kind of coupling occurs between the mode of vibration of this membrane and the mode of vibration of the other membrane. That means that because of the temperature difference between the plates and because of their existence in vacuum, quantum fluctuations cause the hotter membrane to vibrate at a higher frequency compared to the colder one, and at some stage the phonon modes produced in this hotter membrane starts to couple with the phonon modes produced in the colder membrane, and thereby this phonon coupling or phonon mode coupling results in thermal equilibrium or equalizing of temperature between these two plates. Therefore, the temperature corresponding to the phonon modes reach thermal equilibrium. Therefore, one can say that they have attained the two membranes have attained thermal equilibrium. Therefore, there has been a heat conduction mediated by phonon coupling, and therefore it's purely quantum mechanical in nature, and it is not one of the known methods of heat transfer in any materials. So it's a very interesting result that has been reported just this week, 12th of December 2019, in Nature issue, and it's a very interesting result. A prestigious scientific journal, Nature, has reported this. This group at the UC Berkeley, University of California at Berkeley, have studied this problem with great sophistication, equipment, and the data is very clean and results are very well interpreted, and therefore this is definitely a new way of heat transfer. In comparison with the conventional known methods, this is an interesting method. And what are the applications for this? What could be the applications? Because we are talking about nano dimensions, and typically when such coupling occurs, the distance should be less than, in their experiment they observed that it's definitely around 300 nanometers or so. So as the distance between the plates is increased, this coupling becomes stronger, and the transfer of heat between the two membranes happens quickly in a more easier way. So the distance is definitely a factor here in this experiment, and therefore it's very interesting because this study, the experiment that has been carried out in the study, could lead to better understanding of heat transport mechanisms in nano devices. For example, in miniature devices, in electronic circuits, heat dissipation affects the performance of devices. For example, mobile phones. The performance could be substantially improved if the circuits employ very sophisticated heat dissipation mechanisms in these devices, and therefore in nanostructured devices and future electronic devices, heat dissipation would be a major hurdle, and such understanding of novel mechanisms of heat transfer in miniaturized environments is going to go in a long way in improving our devices, and therefore this study has a direct impact on a lot of practical applications in future. Thank you.